Okay.
Joe, are you ready? Okay, good.
Okay. Very formal now.
Good morning, good afternoon, good evening to everyone joining us from around the world. On behalf of the International Society in Quantization, Geometry and Dynamics, ISQGD, it is my great pleasure to welcome you to ISQGD workshop on fractal geometry. ISQGD is truly global academic home rooted in quantization, geometry, and dynamics. And today's workshop reflects our commitment to fostering international collaboration, high-level scholarship, and inclusive mathematical dialogue. We are especially pleased to launch this workshop as part of our continuing academic program, which includes distinguished lectures, special sessions, workshops, and conferences, all carefully archived to ensure long-term academic visibility. I'd like to thank the organizers, Dr. William Origan and Dr. Jichang Wang, for their dedication and excellent contribution in bringing together this distinguished group of speakers. It is now my honor to introduce our first speaker, Zhou Feng from the Israel Institute of Technology. The title of his talk is Dimension of Overlapping Self-conformal Measures on the Plane. Thank you.
So I'm going to talk now.
Yes.
Yeah, thanks, Marina, for the introduction, and thanks to Chang for the invitation, and thanks to all the organizers for making this workshop happen. So today I'm going to talk about the dimension of self-conformal measures on the plane, on the complex plane, especially when the FS contains overlaps, and this is the joint over with the area rapport. So let us first recall what are self-conformal fractals on a plane. They can be generated by so-called holomorphic iterative function system. They consist of finite many holomorphic maps, which means you can find a bounded domain omega in the complex plane, and each phi I is actually a holomorphic injection on a domain slightly bigger than the closure of omega, and we require phi I of closure omega is mapped into itself. And we further require the derivative, the norm is strictly between 0 and 1. And we require this derivative condition is on the closure. Every point in the closure, if you recognize this condition, you will see this f as hyperbolic. And one biggest benefit for that is the bounded distortion. Roughly means the balls are mapped to tomatoes, not the bananas. So this is very nice for us to analyze the shape of the linear set. And we are further given a probability vector, which is the sum of entries that is 1, and we without loss of generality we assume the entries are positive, because if the entries are 0, we can safely throw away the corresponding maps. So the index set is the same, but by the same finite alphabet. So with these two information, IFS and the probability vector, then we can start a random walk. So suppose we are starting from any point in the omega x0. In the first step, with probability pi, we can choose a map phi I. In the second step, we can choose with the probability pj, we can choose another map phi j, and then we repeat this process, and eventually you will end up at one point in the omega. The reason of this sequence converge is our assumption of contracting. So this sequence converge and into the point X, and actually it depends our choice of maps. Since our choice of maps are random, so actually this X is a random point in our domain omega. And what is a self-conformal measure? It's actually the law of these random points. And the self-conformal set is just all the possible location of this random point collected together. In other words, this K is the support of this mu. And this is the way we generate this self-conformal fractals. Let us make this more conformal, more formal. And we can define the so-called coding map. which means you are given a sequence choice of maps. You start from any point, and then this limit will exist, as we have said before. And this is our coding map from the symbolic space to the omega, the geometric space. And actually, I mentioned this starting point is independent. This limit is independent starting point because of contraction. Actually, you can even replace this point with any compact set. So everything will contract to one point by the contraction. And then you can make a further observation that our choice of these maps, they are IID. So if from this assumption, you will see the law of this part is the same of the whole part. So probabilistic, so we can transfer this probabilistic phenomenon into the measure theoretical way. It's just that as we have defined, mu is the law of this pi, and in other words, this is pi is the push forward of this ballooning measure on the symbolic space. And from this property phenomenon, we can see this phi is a p-weighted sum of its images under the maps in the IFS, holomorphic maps. So they are conformal. So we call it a self-conformal measure. So similarly, from our definition, K is the support of mu, and we can even say this K is the image of the whole symbolic space. And from this property, you can see K actually coincides with the union of its image under the maps in the IFS. So this is our object, self-conformal set, and measures. The reason we study it is this is the simplest way to express that one object is made of smaller copies of itself, and they are related to many other problems. We study all kinds of properties of it, geometrical, analytical. In this talk, we focus on dimensional properties. Okay, so this is our object we want to study. I will also going to use mu as a self-conformal measure, k as a self-conformal set. Okay, then let us to see several classical examples. The first one is perhaps everybody knows is Sierpinski triangle. It's made of these maps, triangle contracted by one half, and this piece is contracted one half and move to here and then move to here. So this is made of three similarity maps, FS. And the second is the so-called naming set of a Schottky semigroup, which means in your FS, the maps are Mobius transformation. There's a nonlinear. Nonlinear essentially goes from Z to the 1 over Z, the inversion map. And this Mobius transformation can be determined by 2 by 2 complex matrices with the determinant 1. And we further it is required is a hyperbolic, which means you can find maybe in the Riemann sphere, but you can require the repelling point and the attracting point are actually in the complex plane. And then with this assumption, you will see outside of this repelling point, everything will contract to the neighborhood of a attracting point. So we can find an omega like this, and if we want, we can replace G with some power of itself that makes sure it is stronger contraction. So omega will contract like this, and G2 the same thing. On the omega on the G2 will contract like this and repeat, and eventually we will get this Cantor set. It is also a self-conformal set. The third one is also very famous, is a Julia set. Julia set for hyperbolic rational map. In some case, actually they can be generated. There are several definitions, equivalent definition for Julia set. That in some case they can be generated by inverse branches of your map. For example, here we are choosing a quadratic polynomial with this translation big enough. For example, it is 3. So this is three classic examples of a self-conformal set. And for this self-conformal set, the Hausdorff dimension is well understood by the classical theory. For example, the similarity dimension in this case is open set condition. Similarity dimension is log 3 over log 2. And by Patterson-Sullivan, the dimension of this can be expressed as a critical point of the Poincare series, and also by our assumption this hyperbolic rational map, the classical formula of Bowen regarding the dimension of conformal repellers they apply. So for these sets, you have a well understood of the dimension. At least you can express as some formula other than the definition of Hausdorff dimension. And then our first motivating question is, what if your IFS has overlaps? So what this means? This overlaps means your K, your self-conformal set under the maps in the IFS, they overlap each other in a substantial way. And we will see why this gives us the difficulty to estimate the dimension. Here we just point out what's the meaning of overlaps in these three examples. Okay, in the first example, it's just okay, these triangles maybe overlap each other, and in the second, you can also say these balls can overlap each other. In other words, you can say here we consider limit set not just a discrete group, we consider the no discrete, which means we can consider we want to go further the dimension series of limit set beyond the Kleinian group. And in the third setting, this overlaps means this IFS doesn't have to be a collection of inverse branches of one single rational map. So this is the meaning overlaps for these examples. And another a more general uh, extension what we want is to say, okay, here, 1, 2, 3, the maps are similarities and Mobius transformation, and this is a root function. They are algebraic in some sense, but in general, the hyperbolic maps can be uh, very general. So this is our first motivating question that we want to compute of a more general class of self-conformal set by allowing the IFS, the generating IFS, to have substantial overlaps. So as we have no from the classical theory, the dimension of set usually related to the to estimate the dimension of set, you usually estimate dimension of meshes. So let us move to the second part is the dimension of meshes, in particular the dimension of our self-conformal meshes. We consider which dimension? We consider the so-called exact dimension or just the dimension by a result of Feng and Hu. They prove that we denote this dimension as d mu. They prove that if you look at mu typical point x, then the decreasing rate of mass of this ball centered at x with radius r, as r goes to 0, this rate, decreasing rate of mass, they exist. This limit exists and a constant for typical points. So this is what we call this, why we call this mu. It's exact dimensional. And we denote this typical constant as d mu. We call it a dimension of mu. There's if your measure mu is exact dimensional, there are several advantages. One is that there are many common user notions of dimension that coincide, especially as long as your dimension only care about the typical points. They coincide. The two, I like just pick up two examples. The first example is the so-called lower Hausdorff dimension. This is defined to the smallest dimension of a set that you can see with your measure. So this is connecting the dimension of measure to the dimension of set. And also they coincide with the so-called entropy dimension. This is defined to be the growth rate of your entropy. This entropy mu with respect to partition. Here dim n is a dyadic partition with side length 2 to the minus n. And this is the definition of partition. You get a measure, you get a partition, you cut your measure according to this partition, and then you feed the mass of the element into the classical entropy function, and then do a summation. This is our partition entropy. And actually, our major quantity is this entropy. We want to estimate about the behavior of entropy on the different operation and different scale to get our proof. So this entropy is very important for us. Entropy characterization for the dimension is very important. So this is a dimension of measure. And then we look like the two other quantity, which is the Shannon entropy and the Lyapunov exponent. You can see the formula here. Entropy, Shannon entropy is summation in similar way to the partition entropy, and the Lyapunov exponent is somehow you can understand the average contracting rates. The reason that we introduce these two quantity is that together they can make a natural upper bound. So how do we get this natural upper bound? As we have seen that the dimension of measure, you look at multiple point, it's same here. You look at the new typical point x in your self-conformal set K, and then do nth iteration, then you will see overlaps. We don't have separation condition like the classical case. The sine set of which means phi u if this is the final word, this is my notation for abbreviation of this composition. So this phi uk we call the sine set. The sine sets may overlap, but at least one single set because we choose x in K. At least one single set will cover will make the x stay inside, will cover this x. So by the limit series, you see the mass of this potato is decreasing with the rate of entropy, and the diameter is decreasing with rate of the upper exponent. Then you combine these two facts into the definition of a local so-called local dimension. Then you will get an upper bound because here you get the upper bound of mass. So uh, so you just plug into the definition, and the denominator is a negative. The smaller mass, then you get the upper bound. So you plug this mass here and diameter here, then you are and net n to infinity, then you get this upper bound, entropy over chi. This is the natural upper bound. One part of natural upper bound is entropy over the upper exponent. Actually, there's nothing stop us to further consider nth composition of your FS, which is defined as follows. You collecting all the nth iterations of your maps together. Remind, please be careful that here is the notation of a set. So for this notation, you have removed the redundancy. So there are two maps, but they coincide, may coincide each other, but we throw it away. However, then the weight, the probability will change correspondingly. That's why we need to consider this kind of uh, uh, discrete probability measure. This serves as the same role of the probability vector in the first our original FS. This is defined as follows. So this nu is just the discrete mass measure support on the maps in the FS and give the weight of the corresponding probability vector. Actually, we call this as a driving measure. So you are given a FS plus a probability vector is the same thing you are given a driving measure for the random walk. So you given this driving measure, and then you do nth convolution. This convolution is the pushable of your product measure on the composition. And by this nth convolution, you are considered coincident. So if your two maps are the same, the weight will put together. So this is the new weight you should consider. And the Lyapunov exponent becomes n chi. And sorry, there's an energy saving mode of my lights. So I need to move. Okay, so then you get this upper bound by the same procedure of analyze. Then you like n to the infinity, you get a so-called this part you get so-called random walk entropy. Then you get a new more refined upper bound by further considering the by further encoding the coincidence of maps. So this coincidence of maps is the another term for the exact overlaps. So you got this upper bound, and then you combine this upper bound by the fact that actually our measure is supported on a plane. So you get an ambient space upper bound. So you combine together, get this natural upper bound. So this is a procedure that we get is a natural upper bound. So I would like to further analyze and to emphasize this picture that here this upper bound is just by just picking one single map or one single set and as a mass and a diameter, and also even this refined upper bound you just consider exact overlaps. So the single maps that they overlap substantially but not exact overlap, this the information of this kind of overlap, not exact overlap, but substantial overlap, are not contained, are not considered, are not included in the our this natural upper bound. And at the first glance, this kind of stuff, right? You look at the picture, at the first glance, you will believe that okay, this overlap will make the estimate of the balls, the ball, make the mass of the ball to bigger. So then your the mass cannot decreasing too fast. Then which means this will force the dimension to be dropped. But this is the first impression in in our overlaps. So this is my since I want to emphasize here this natural upper bound, they just consider the one single map and plus the exact overlaps. This substantial overlap they do not consider in this natural upper bound. And our natural question is that when this equality holds. So this has motivated many recent work towards the dimension theory in the overlapping IFS. And actually, the recent works for this question, they show somehow they call the dimension rigidity or just the rigidity phenomenon. So actually, the rigidity rough means that rigidity happens everywhere in mass. So rigidity rough in human terms is that you get something more than you expected, you get some surprising stuff. So this rigidity in our setting that means that the equality will hold if you can we just destroy exclude some very obvious obstructions. Here this is the ambient space, and this obvious obstructions roughly means if your set and measure are trapped in some sub shapes, sub geometrical configuration, somehow in this sub shape will force your dimension to be some dimension strictly less than d, some integer. Um, and I would like to say more that because I have explained why this natural upper bound and why this equality will, why this fact usually will give you a surprising stuff. Because the left hand side, this is geometric information, geometric dimension, as we have explained. You believe that these overlaps will give some dimension drop because it give more mass to a one ball, but actually you just destroy this obvious obstruction, and then the equality holds. But at the right hand side, you do not consider this kind of substantial overlap, but not the exact overlap. So the exact overlap information is already encoded into the random walk entry. That's why it's very surprising. Surprising stuff is interesting stuff. And okay, this remark I have explained because the overlaps somehow if this that you believe or somebody prove this dimension rigidity, then the substantial overlap but not exact overlap, they actually doesn't affect your dimension. This is very surprising, and we call it a phenomenon because there's a conjecture in this topic, and there's substantial progress in last 20 or 25 years, 20 maybe 20 years. And this is so-called exact overlaps conjecture. It is conjecture for every subsimilar measure. So we call it subsimilar if the FS are considered similarities. If for every subsimilar measure on the real line, there's no other assumption. The geometrical dimension well equals the this natural upper bound. So this natural upper bound, they only consider the exact overlaps. There's no this substantial overlaps. So it's quite surprising. And this is a conjecture, and there's substantial progress towards this conjecture, but this conjecture is still open. Anyway, our result is also motivated by this kind of rigidity phenomenon. So let us recall some progress towards this conjecture. The first substantial and breakthrough and seminal work is due to Mike Hockman. He introduced a method of eddy combinatorics in the field dimension theory of IFS. He proved that this conjecture is true if you assume this IFS to be exponential separated. This exponential separated is mild and checkable. The rough means you can allow your single set to be overlap a lot, but you as long as your lower bound the distance is the lower bounded by small number c to the n is the level of this single set, then you can call it exponentially separated and the conjecture holds. Actually, this conjecture in this format it holds uh, for as long as is verifiable. For example, if your conjecture rate and the translation they are all algebraic numbers, then Hockman proved your conjecture is true. So that's some other progress towards this exact overlap conjecture. I would like just point out, pick up several to make you even more surprised by this rigidity phenomenon. The first one is the breakthrough of Peter Value. He proved that the transcendental Bernoulli convolutions, overlapping Bernoulli convolutions, they have the dimension one. And the other two, this is by area report. He proved that actually you don't have to assume all the parameters to be algebraic. You just need to assume the contraction ratio to be algebraic, and there's no assumption or translations. And then your conjecture is true. And the reason why his result is very surprising is that the combine his result with the examples provided by Simon Baker. Actually, Simon Baker constructed example that the contraction rate is algebraic and translation may be transcendental, and then the overlap can be substantial. So this overlap can be any function of the level of your n. So even in these substantial overlaps, the conjecture is still true. So I hope this kind of progress can make you that think the exact overlap conjecture may be true, but actually we don't know. We don't know. The conjecture is still quite open. And for the recent progress, you can see a recent survey of Peter Wadu. So this is the self-similar IFS on the real line. And actually later, Hockman extended his result to the higher dimensional Euclidean space. But in higher dimensional, as you can see, the dimension rigidity, you have to destroy to exclude some overfield of obstruction. Here, for example, in the plane, there's two category of obstruction. I will explain this two category of obstruction. This is a phi reducibility, which means your phi, your fs, will preserve a single point or a phi line. Then under this phenomenon, your measure are trapped in these shapes. So the dimension of this is always less or equal than 1, but it's very easy to make this natural upper bound to be bigger than 1. So this is the phenomenon you have to destroy. The second category of phenomenon is called saturation. Saturation is this kind of phenomenon. You get a bunch of parallel lines, and then they seated on a candle set. This candle set has dimension strictly less than 1. And if your IFS preserve this kind of geometric configuration or lamination, and then you will see that the fibers are trapped by this geometrical shape, this fiber 1. And then you will see geometrically the dimension of measure are trapped in this shape. So this is one plus a dimension strictly less than one. And then your geometrical dimension is always strictly less than one, but it's also very easy to make this upper bound to be two. Sorry, two. Did I say one? This is two, two. So this is also the phenomenon you have to destroy. So in high dimension, you cannot just make the conjecture that this equality always hold by replacing one with some d. You have to destroy some obvious obstruction. This is two examples. And actually, this phenomenon, one way to destroy this phenomenon is so-called irreducibility. So in subsenior case, this means there's some non-trivial rotation part in your similarity map. And this is also the similar condition we want to assume to destroy this kind of a non-linear version of this saturation. So this is the similarity world. And then you may wonder whether the result can extend to the non-linear world. So one step towards the non-linear is a projection fraction linear transformation or Mobius transformation. This is a setting of projective nonlinear and contracting on average case. And in this case, your IFS consists of Mobius maps, and these Mobius maps are defined by SL2C matrices, and you can assume some very classical condition due to Furstenberg, which means strongly reducible and proximal. Roughly, it means the spread out, and this proximal is contracting in some contracting in the projective setting. And in this setting, you cannot hope the contracting everywhere because your matrix is anyhow you have this repelling direction. You can only remove this part, then everything else will contract to your attracting line. So this there's another additional difficulty in this setting is the contracting on average. But anyhow, in the classical result of Furstenberg, he proved that this coding map actually in this setting is called a Furstenberg boundary map. This is well defined for beta almost every sequence of choice of in your symbolic space. Then you can define the image measure pi beta. It's also a station measure, the unique station measure for this phi and the probability vector. And this is called a Furstenberg measure. So in this projected nonlinear setting, Hockman and Solomiak, they prove that if okay, this is a phi can be in general SL2C. If they prove that if this IFS is contained into the real matrices, and in this case, your IFS preserve this real projective line, and just stay in this big circles, and they assume this very weak Diophantine condition. We will define this condition accurately later, but now you can just understand this as some the exponential separation, but you allow exact overlaps, and this condition can allow substantial overlap. So this is different from discrete group or open set condition or other very strong separation condition case. So under this mild separation condition, they prove analogs of the dimension equality. So dimension of mu equals random walk entropy over this 2 chi. This is 2 chi is the right rate of the contraction in the projected setting. This difference of your two Liouville exponent, and as we can see here is one. So that's why there's a one here. And later, actually, very recently, Rapport and Ren they prove a general case if phi is a SL2C on the same weak very mild separation condition. Also, this very classical SIP condition, and they have to assume this necessary obstruction to exclude this necessary obstruction to gather the expected equality. But you have in this case you expect the lateral upper bound replace 1 by 2 because you measure leaves the whole remain severe, and you can see if you preserve this generalized circle, then your measure will trapped in one dimensional object. So this is the obstruction you have destroyed. So any case, I want to express that in high dimension, you have to destroy this kind of overfields or some kind of algebraic obstructions if you want to make sure your measures is very, very spread out. So, so now we move to the analytical nonlinear. This is the breakthrough of a rapport. He proved that in this very, very general nonlinear, for example, here in this setting, the holomorphic, the real analytical F maps, they constitute a infinite dimensional vector space. It's different from the SL2C case. SL2C is finite dimensional. Even in this case, he proved that if your FS preserve a real line and you assume a very minor separation condition and it do not preserve a single point, then your dimension equality holds. And in some sense, you can uh, imagine this is the obstruction, zero dimension obstruction. You have to destroy this. And of course, now the state of art, we didn't go to fully dimension rigidity to fully remove any to without any separation condition, but the state of the art to assume very minor separation condition. So now we are ready to move to our major result. Is the holomorphic extension of Arieta result to the plane. And in this setting, you will see the obstructions. Here you have an analog of a phi irreducibility. You have say this phi cannot stay preserve a single point, and actually in the non-linear holomorphic setting, this kind of phenomenon may happen. So this phi may preserve a analytic curve. Here, analytic curve, we assume our definition of analytic curve is the embedded one-dimensional real analytic submanifold of C, which means locally you can find a biholomorphic map to the real line. So this is also a phenomenon because your mesh are trapped in one-dimensional object. You have to destroy this. And the other is the analog, nonlinear analog of the saturation. You can push forward your measure by this holomorphic map, and then the saturation, the similar contradiction argument, you will see that this is the phenomenon you want to destroy. So these are two type of phenomena you have to destroy if you want to extend that, get some up some analog equality if you want to replace 1 to 2. So then we are almost ready to state our major result. Then we define the separation conditions, the minor separation conditions. So we denote this as the supernorm of a complex function of our domain, and we call this FS weakly Diophantine. If you can find a very small c and at the infinite many scale, and you look at the n-nth word, and you only look at the words that with a different composition of map. Actually, the difference is lower bounded by c to the power n. Intuitively, just the largest part is lower bounded by c to the power n, and exponential separated is similar, but you have to make sure every distinct word the corresponding separation holds. So this exponential separation separated is stronger because you check more words, more pair of distinct words. And our no exact overlap is just you can say every distinct word get composited to a different maps, or you can say the semi-group generated by your IFS by composition, they are free. It is free. And the remark is that the exponential separation is equivalent to say the IFS is a weakly separation, but you do not allow exact overlap. This is very similar to say that the weak separation condition is just open static condition, but you allow exact overlap. But be kindly reminded that exponential separation is much weaker than the open static condition. So now we are ready to state our major results. Our major result is as follows. Let me state everything slowly. So you have a IFS phi holomorphic on a domain, and then you give a positive probability vector, which positive means entries are positive, and that mu denoted the corresponding self-conformal measure. We assume phi do not preserve a set E means for every phi of E is contained in E for every maps in your FS. This is the meaning of preserve. So phi do not preserve any point or any analytic curve which are closed in omega. And you also assume the condition one, condition two, phi is not homostatic in some sense. It's not a holomorphic conjugate to a homostatic because we can see the non-linear version of a saturation. You can conjugate. Okay, so this condition two means you cannot find any biholomorphic map such the conjugation of your FS consists of homostatic maps. Homostatic means similarity, but there's no rotation. So the linear part are just real numbers. So, and then the third we assume some mild separation condition. So the state of that it allows mild separation, but we still cannot do the completely remove the separation yet. So under this assumption one, two, three, then you get your expected dimension equality. Um, and the remark is that the condition one is necessary because condition one is used to destroy this obstruction of this phi irreducibility. This is necessary. The second is that you want to destroy this kind of saturation. That's no. This is the basic the just like similarity case, the irreducibility can destroy this saturation. This is basically under this relatively more checkable condition to destroy this saturation phenomenon. So we call it essentially necessary. And regarding to assumption three, because if you believe this dimension rigidity or exact overlap conjecture, you may believe maybe we can completely remove any separation condition. But this is well beyond our research because even in the real line, in the self-similar case, the conjecture is still open. But in any case, we can relax, we can deal with the substantial overlapping case. So this allows you to compute the dimension of many overlapping self-conformal measures. So this is the title. So this is our major result, and then we can see some applications. The first application or corollary, in some sense, gives the even more checkable condition for the assumption for our main theorem, because the FS do not preserve a point is the same thing that the maps in the FS do not share a common fixed point. So this is very checkable because you can check the fixed point or whether just find the many maps, check the fixed point whether they are the same. The second is the analog of irreducibility in the self-similar case. It's just no linear version of the reducibility. You look at if you can find a word, a final word of the alphabet, and the corresponding maps, the derivative at the fixed point of this map, they're not a real number, they're irreducible. Then under this assumption, then you can say IFS cannot preserve an analytic curve and cannot homomorphic conjugate to a homostatic IFS. So this makes your assumption even more checkable. And regarding the third separation condition, as we have mentioned, the exponential separation is stronger than weakly different time. It's just weakly different time, but without exact overlap. So without exact overlap, then on that setting, the random walk entropy becomes the Shannon entropy. So Shannon entropy is much more computable, and then random entropy walk entropy is also more computable compared to other like Furstenberg entropy contain the overlaps. So anyhow, in this assumption, your entropy part is even clear, and this is stronger than weekly different time. And actually, a recent work of Balas Barani and Istvan Kroswawi and Sasha Trochet, they provide a very explicit criterion to say the real analytical IFS in the setting of area purport in the real analytical case, they can check the exponential separation. Actually, their criterion can tell you the exponential separation is very minor in topological sense, and we believe their result is very likely to generate to the holomorphic complex case, but we do not pursue that. So this is the more checkable condition. And the second corollary is regarding our first motivating question. So we can compute the dimension of set now. So under the same assumption of corollary 1, you can say the Hausdorff dimension of K equals minimum of 2 is the ambient space, and the so-called conformality dimension. This conformality dimension satisfy the Bowen's formula is a zero of a topological pressure. So originally this equality holds in the open set condition, but now you can say this equality holds under this mild exponential separation condition. It allows substantial overlaps. So this is dimension of set. Now the third application is or corollary that we have these two corollary regarding dimension of a set measure and set self-conformal set and measures. Then you can combine a recent recent result of Solomiak and Takahashi. They verify the exponential separation in a nice no degenerate real analytical and some very minor assumption of your one parameter family of fs. They verify this exponential separation in that family. Then you can combine their verification of this. They prove this exponential separation holds typically. Combine this result with our query, you can say the dimension equalities, like here for the set or the here for the measure, they hold typically in a one parameter family of holomorphic IFS. So this is the application. So this is basically end of the story part. And we would like to talk about a little bit about the rough ideas of the proof. So for the proof, as like many recent advance to this overlapping the overlapping IFS dimension theory, you realize this additive ingredient, which is the so-called entropy increase. The very rough idea is that you have your measure here, and then you iterate, and you pick. So if you assume, maybe I should just write a one-dimensional case. One-dimensional case, you iterate, you get many Zener map, and the left endpoint, and by our assumption of this is that you want to get a contradiction. The proof is final argument is contradiction style. So assume by contradiction your dimension drop, which means your dimension equality do not hold is trickless. Then you will find at some positive proportion of this combined with your separation. This atomic measures has a positive entropy. If you look at the final, because they are exponential separation, you can move your scale to m times n, then you find the positive entropy, and then this atomic measure conform the smaller copies of your mu. This is just this is mu, just a smaller copy of mu. Then there will be a substantial increase, and this increase will give you a contradiction because you can write some by the stationarity and the concavity of entropy. The left-hand side is your dimension. The right-hand side, because your positive proportion of your acting discrete measure of entropy and conform your smaller copy, produce a increase. So the right hand side is a strictly less strict, but concavely this should be the greater or equal. But left hand side is actually bigger than your dimension. So this is the rough idea of final conclusion argument. So and this argument trace back to Hockman, and then it has been developed for in many different works. Now actually, finally, in our proof, the format in that case is developed in the paper of Hockman and Rapport regarding the overlap set of fine uh, sets in the plane. And then, so now you know you have to build this kind of entropy increase. But however, in our case, this holomorphic maps is like a real line case, is infinite dimensional. A big important technique in the paper for a year is that this infinite dimension, you cannot even know how to even quantify the in a scale, in a finite scale sense, that the entropy of this is positive, and it's quite complicated to build an entropy increase for this acting measure in this infinite dimension space. So the technique of Arya, he proved that you can actually replace this measure by its Taylor approximation, taking on the support of this measure to get a measure on the finite dimensional space, this space of polynomials with degrees k, and the coefficients are complex. So this is a 2k plus 1. Anyhow, this is a finite dimensional space. And for this measure, then you can build the corresponding entropy increase. So this is why we can reduce our goal to prove. Actually, this is also important to assume homomorphicity or real elasticity, because you have to make sure this approximation, the error is controlled. So this is one part we use this and tennis and neticity, and then reduce the problem to the entropy increase. But this entropy increase is for a nonlinear action by the polynomials. So for this kind of nonlinear action convolution, nonlinear convolution, you cannot directly to apply the entropy increase or the inverse theorem for entropies in the higher dimensional of Hockman for the translation convolution, the traditional convolution in the plane. This is defined by translations. So the idea, the technique method is also appear in many other papers. The idea is the strategy is linearization, and then we want to invoke this uh, uh, entropy increase or inverse theorem for the translation in the plane. So in the plane, because you want to build this kind of entropy increase, according to the inverse theorem of Hockman in the plane, there are several phenomena actually prevent you get this entropy increase. This is a one phenomenon. If your acting measure is arbitrary, but your base measure, your theta, is almost full entropy. So there's no room for you to increase entropy. So you cannot get this kind of entropy increase. So you have to clear. So the rest of this part, you have to verify the conditions of Hockman's entropy increase. So you have to clear this kind of bad situation. This can be achieved by so-called uniform entropy dimension. We prove this uniform entropy dimension. Actually, this is for the mu. Actually, in the actual application, it should be some a mild distortion of mu. So we proved the uniform entropy dimension. This can be destroyed, this phenomenon, by plus our assumption d mu is less than 2. So this can be destroyed. And this part, the argument traces back to Hockman, but this we relied on one ingredient is that actually under our assumptions, mu do not charge any analytical curve without any separation conditions. So this is this phenomenon you have to destroy. And the other phenomenon is the so-called saturation. So this is another saturation. This saturation is the saturation that will prevent you get entropy increase. And you can see if your acting measure is like this, is parallel to this measure, you will see that your measure is like this and almost full entropy along this direction. And you acting by translations. So you will feel that there's no room for you just increase the to increase entropy. So you have to also destroy this phenomenon. So this phenomenon only happens in the plane. So in several previous works, they in some of them actually deal with this planar case. Others transfer the one dimension case. But in our setting, we have to confront this uh, no saturation, the saturation phenomenon. We have to destroy it, and the strategy is adapted from the recent work of Robert and Ren, and they prove this Riemann sphere case. The one key ingredient in this strategy is the so-called direction cocycle. It's not co-boundary. This is used to prove some sequence of directions. Then you do not concentrate to any single direction. This is one key ingredient to get this make this strategy work. And the difference that in the complex Riemann sphere as 2C case, you can take a derivative. You can have many explicit you can take derivative and many explicit stuff, and the shape you want to destroy is somehow more rigid than an analytic curve. They are generalized circles. So in our case, we cannot do that, but we use anyhow we achieve this goal using complex analytic arguments. Actually, complex analytic arguments has been used several stages. For example, here and also final arguments and in many different stage. And yeah, I think this is basically the rough idea of proof. And thank you for listening. Uh,
Okay, thanks very much for those for his interesting talk. I think maybe there is no time for question. Maybe uh, I this talk should end at this. Is it okay?
uh, I didn't understand what's the last sentence?
I think maybe we should end this talk at this time.
Okay, okay. Yeah. Thank you.